here's the problem that this video is going to be talking about. How long is the coast of the United States? If you look at any map and see America, you might think that it's easy. Just measure the outline of the country and you have your answer. Several people and organizations have already tried this though, like the Congressional Research Institute that calculated it to be 12,383 miles, a second study from them that changed it to 29,093 miles, the CIA puts it at 19,924 miles, and a study from NOAA calculated the shoreline to be 95,471 miles. You may have noticed that all of these numbers are different, which is weird because they're all just measuring the same coastline. So what's going on? Let's move over to a smaller country like the United Kingdom and measure the coastline of Great Britain to get a clearer picture. Obviously, the coast of Britain isn't straight. Every time you look closer at a line that looks straight, you'll see more curves and bends. So how do you measure the length of the coast if every time you look more closely, it never actually becomes straight? You end up using the smallest measurement unit that's feasible. So if you were to measure the British coast using lengths of 100 kilometers, you'd end up using 28 of them and get an answer of 2,800 kilometers. But if you shortened your measuring units down to 50 kilometers, you'd end up using 68 of them and get an answer of 3,400 kilometers, which is 600 kilometers longer than your first measurement was. This is called the coastline paradox, and anybody's answer to how long a coastline is depends on what size of measurement they're using. First observed by a guy named Lewis Fry Richardson back in 1951 as a way to explain how Portugal and Spain had come up with totally different answers to their mutual border length. The coastline paradox has been annoying cartographers ever since. Basically, the smaller the unit of measurement you use to measure a coastline, the longer your answer will become. You could theoretically go all the way down to the molecular level for your measurement unit, but if you do that, the length of the coast seems to approach infinity. It doesn't seem to make any sense that you could have a defined space with a finite area like Great Britain be surrounded by an infinitely long perimeter. But there's a similar concept that can be found in mathematics called fractals. A Koch snowflake is probably the easiest way to visualize this concept. So imagine a triangle with equal sides of 1. Put another triangle on each side with equal lengths of 1/3. You can keep repeating this process forever, and if you zoom in on the snowflake, it essentially goes on forever. When you zoom back out to the original starting point, you're left with a shape that has a finite area, but an infinitely long perimeter. A lot of coastlines around the world have similar properties to this, so you can keep zooming in on the coast of Britain, and the coastline will continue to look roughly the same no matter how far down the rabbit hole you go. As mentioned previously, you'll eventually hit the molecular level if you zoom in far enough, and you'll be measuring a beach by counting atoms. If you did this forever, you'd find the coast of Britain to probably be millions of kilometers in length, which just isn't very practical or easy to understand. There's also the minor problem that coastlines tend to change all the time with erosion. Every time a wave crashes on a beach, its shape is changed by a little, and that is really hard to accurately pin down. On top of this, sea levels are rising around the world, which can drastically alter the way a coastline looks. In extreme cases, like what might happen to the Maldives in a few decades, entire land masses may become completely swallowed. On the other hand, there's the Dutch, who have been adding land to their coastline now for over 700 years. The point is, Earth is constantly evolving, so good luck going out to a coast with a microscope and measuring the length that way. Every number you see online or in a book for how long a coastline is basically just a guess or an estimation. The true value is impossible to know, and that is the coastline paradox.
Now back to your little map. Where's the scale here? Why do you never include one? Is it because it's impossible? Yes, that is exactly why. And if you disagree, here's your challenge. Pick some distance on this map, a centimeter, an inch, whatever. Tell me the distance it corresponds to in reality. Then pick some cities and use your scale to estimate the distances between them. Pick 2 on the same continent. Pick 2 on different continents. Use it to tell me how wide this inappropriately enormous ocean is.
So far we've been told 37,560. We've been told 43,400. But if we just look at Pigafetta's own writing, where he says that land leagues are of 3 miles and sea leagues are of 4 miles. So that gives us 1460 times 4 is 57,840 miles. Yet we've seen other articles try and tell us 37, 47. It's actually 57,000 miles. Now when you look at the logbooks of Captain Cook, his logbook for his second journey was also 60,000 plus miles. You could look at the British Challenger expedition in the 1800s. That was also over 60,000 miles. So we should start being able to recognize a pattern here that obviously when we circumnavigate south of the equator, we are logging way too many miles. Remember that they're at the bottom of the globe. So if the equator is 25,000 miles, how are Captain Cook, Magellan, and others doing 50 to 65,000 miles, which is more than double?
Use it to tell me how wide this inappropriately enormous ocean is.
Now here's what we know now, that there's a 150 mile per hour tailwind. So here's what you have to believe. Either you believe in the globe and you think that that plane is going 415 miles per hour, which is the most ridiculous nonsense. The plane can go 650 easily. So do you think it's going 415 miles per hour, or do you think that it's possibly going 565 plus the 150 and actually going 715 miles per hour? You know, which one do you think is true? They're saying that they go 415. That's what they believe. That's what you have to believe, because this is going in 65.
Well, they have to go. They have to go back. They have to go back the opposite direction. What happens then?
Let me, well, yeah, I mean, that's part of it. But here's the other thing.
That flight takes 14 hours.
Here's the other thing.
Well, so are yours, because you're asking Jetstreams.
Yeah, Jetstreams are real.
Let Darren respond to Darren's answer, because he has a good answer for this. And I'll just throw in there that these flights are not regular. They vary by 5 or 6 hours sometimes.
Yeah, Darren, you just said they're the same. Darren, going from Sydney to Santiago takes 11 and a half hours. Going back takes 14 and a half. So those are not identical flight times. It's because one has jet streams, one doesn't.
Use it to tell me literally anything about the distances between literally anything. When you can't do it and your numbers do not correlate with reality in the slightest, recall that this map does it just fine, and then admit that your map is stupid. Then admit that your map is stupid. Then admit that your map is stupid. Complete inability to make any kind of remotely legitimate map single-handedly proves the Earth isn't flat. But let's continue just for fun.
We do believe that this globe is correct, even if, I don't care how many classrooms you put it in if it's wrong. Here's another thing. Take NASA's own app of real-time data, Earth Now. And it shows these satellites, pretty little dots going around, but when you scroll around, you notice these kinds of artifacts where things knit together and then there are voids. The biggest void being, guess what? You guessed it, Antarctica. It's not enough that they hide it in clouds at a ridiculous rate, but it's just flat out blacked out. I mean, come on.
That's why I know we haven't been to the moon.
So let's take maps, real-time maps of wind, okay? I think these real-time maps are a little bit more telling, perhaps, than the other ones I showed you. So if you look on the left, there is your globe. And you look at the winds on the left, and they swirl around nonsensically. You look at the map on the right, and you have swirls. Those are storms. But you see that everything's going around in a more sensible manner. And it speaks for itself, but just a little more information. The one on the right is basically, it's your flat Earth map. Now, it's not exactly correct because it's the AE map, which A is for azimuthal and E is equidistant. So it's stretching around, as you can see. It's as close as you're going to get to the flat Earth map. And on the left now is the Mercator, and it's just a screwed up. So that model is a flat stretched version that is the most commonly used, but it may be the most stupid of them all. But either way, when you're mapping the globe, it's stupid. When you have the azimuthal equidistant map, as you see on the right, which is what they use in military planning, it's what they use in a lot of route planning when people are in the know, it is a lifesaver, and it's literally a killer if you navigate according to the globe. Now, it's important to understand that the longitudinal lines, the coordinates in the southern hemisphere, are slightly off. They're slightly wrong, and that is key to understanding how the deception is made and why they have problems with Google Earth, why they have problems navigating and flying in the southern hemisphere, in the southern latitudes. And that explains why those of you who know, those of you who have sailed a ship in the southern hemisphere, southern latitudes, away from the continental lands, you have to cover a lot more distance than is expected by the maps or any of the maps that you're allowed to use. And they chalk it up to currents, they chalk it up to wind speed, they chalk it up to all kinds of different things. But the fact of the matter is, since hundreds of years ago, it's very well documented that sea captains and people have always remarked that it's, you know, when you're down there, life's a bitch. You just can't seem to do anything right, and you're out of reckoning every day. And it's something akin to a percentage around, I'm just reaching for it. It's something like 10, 12, depends on how far south they are, but you always have to cover more distance than you physically cover more distance than you seem to have to do on the map. Now, here is a map of the flat Earth. This is one of the oldest ones that there is. You compare that to the ridiculous globe cartoons of today. and you look at the actual photos of today, and you see that when you have things like these routes that don't make sense, you slap it all onto a flat map and it makes perfect sense. Now you can ride on a plane and look at their map, and they try to make it seem like it's a straight flight. They try to make excuses about it, but that's only because of the map you're using. If you take that and you put it on an actual globe and you plot the points out, you'll see it's a weird line that they do.
Use it to tell me literally anything about the distances between literally anything.
I'm looking at is if there's any funny business going on, which I know that there is because of that curve, and how will it look on a flat map. Well, I'm going to draw it out right now and we'll see. Okay, so take a good look at this, and voila, you will see here how it would look on a flat map. But I'm also curious about the globe. How would it look on a globe?
Well, as you can see on a globe, just like this map, it really doesn't make sense. So here we're seeing one big curve up, okay, up and over. And on the globe we're seeing that, but then it juts over to the side, kind of strangely.
And here's where the programming kicks in. UAP, you are so stupid. Don't you know that you take a classroom globe and you take a string on it, and you put the string on one point, and you put the string on the other point, and you tighten it up so it snaps against that glorious globe. And that's your flight path, you stupid, you idiot. Hey, look, I know. I too have been in a classroom for more than a few hours. And it's not explaining it really. Now, do I expect to see perfectly straight lines on either map? No, I don't. But the flat Earth map has straighter lines than your globe map or your globe map derivatives.
Then admit that your map is stupid.
This is a woman that gave birth on an airplane. This was back in October. This isn't even a new story. But I'm not going to play the video because I don't want any copyright problems. But here's another one from CNN too. It's a legitimate story, so please look it up. The story is they were going from Bali to LAX. They had to make an emergency landing in Alaska because a woman gave birth on a plane, which is kind of a cool story anyway. But there's a problem with this. This just says they landed in Alaska, but you can do a little searching to find out that they landed in Anchorage, Alaska. So if you look at that on a map, Anchorage, Alaska is up here off the coast of the tail of Alaska, I guess. It's where the water meets the land right here. That's where Anchorage is. The problem I have with this story is that if we live on a globe, flying from Bali to LAX and having to make an emergency landing way up here in Alaska doesn't make any sense. This scale down here is 1,000 miles. So at some point during this flight, supposedly, when she had the baby on the plane, they had to make an emergency landing, what, 2,500 miles off course? I mean, more than 2,000 miles off course, no matter where they were, to get up there. Does that make sense to you? If we live on a ball, this has to make sense to you. Let's just say they weren't going to LAX. Let's say they were flying to Alaska. Well, when you book a flight from Bali to Anchorage, look at this. The 19-hour flight goes to almost a full day. But that's where they made their emergency landing. So they go from this. She has a baby at some point on this flight. They need to make an emergency landing. So they zip up here. I wonder how fast they landed in Alaska. I wonder how long they were actually in the air. Because if this flight was 19 hours and they had to stop prematurely, I'm assuming they were in the air less than 19 hours. Wouldn't you assume that? Would you assume that they kicked up their flight, 4 hours or so? Yeah, me neither. So in thinking about this, I looked at it in a different way. If you look at it on a flat Earth map, and you're going from Bali to LAX here in Los Angeles, Anchorage, Alaska is on the way. So if somebody had a baby on the plane and they had to stop somewhere, this makes perfect sense. Again, if you're going from Bali to Los Angeles and someone has a baby on the plane and you have to stop somewhere, wouldn't you think an emergency landing would look more like this than like this? I'm not saying this map is perfect. How would we know? The people that can get up there and look and see are lying to us. But I'm saying this makes a lot more sense than this.
And then admit that your map is stupid.
Qatar Airways flights QR725 made an emergency landing in Moscow in April of 2016. A teenager from Saudi Arabia fell in coma aboard Qatar Airways flights QR725, which departed from Chicago towards Doha, Qatar. The online news website Express UK reported that a teenager from Saudi Arabia on board flights QR725 had toxic shock syndrome and hypothermia. After the teenager fell into a coma, the captain decided to make an emergency landing. Where the plane landed is where the argument Flat Earth versus Globe Earth started. The plane landed in Moscow. It doesn't really make any sense at all. However, when plotted on the Flat Earth map, this flight makes perfect sense, as the Flat Earth map shows that Moscow is located directly between Chicago and Doha. Looking at the playback video from the site Flight Radar 24, we see QR725 flying from Chicago to Doha. We can track the flight path. The airplane was flying directly over Slovakia. There were many options for the pilots, stopping in Austria, Germany, France, and Italy, but instead, the pilot decides to stop in Moscow, which is located 1,600 kilometers, as we show here on the globe, and we calculate here on Google. This equals to 1,000 miles away from where the plane was flying. Now remember, this is an emergency landing. The boy had been to a coma. Why would the pilot fly another 1,000 miles or 1,600 kilometers to stop in Moscow? It makes no sense on the globe Earth. But when we look at the Flat Earth map, we understand why the pilot stopped in Moscow for this emergency landing, because he was flying directly above Moscow when you fly from Chicago to Doha.
Then admit that your map is stupid.
Several countries are flying their citizens out of Wuhan, including the United States. A plane carrying more than 200 Americans out of China just landed at an Air Force base in California. The passengers are mostly staff from the U.S. consulate in Wuhan, as well as a handful of other Americans. It was chartered by the U.S. government. It made a stop in Alaska for refueling, where passengers were screened for any signs of illness.
Then admit that your map is stupid.
The distance between Sydney, Australia and Nelson, New Zealand on the ball Earth, given their coordinates and sparing you the spherical trigonometry, should be 1,310 miles. But the Australian Handbook, Almanac, Shivers and Importers Directory states the measured distance as being 1,550 miles, which is a full 18% longer.
So now, about Australia. if you look at Australia on the globe, it looks round-ish, okay? And they talk about the sun and how the flat Earth map doesn't work with Australia. And I'm just going to address that. You have Australia, and it's kind of the shape like it looks like on the globes, and it's really hard to ascertain the true distance. We know it's probably longer than what they show, and that is for several reasons. I won't get into all the reasons, but they are plenty, and that is one of 2 books that I'm working on writing, because it's such a heavy topic with so much information, and it's one of the things I cannot tackle. It's the only thing I think that I just cannot tackle in one video, to have that explanation done. It's just too monumental. I have to do a book because it has to do with so many calculations and latitudes and longitudes and anecdotal things. It's one of these things that has proofs, but it's such of a huge issue to tackle with geography that any one proof is not going to be enough, because there's so much evidence. It's one of these things to overcome. I mean, like the flat Earth issue itself, you can't solve it in one shot, So the book will allow the reader to go through and reference back to things and kind of work things out so that the preponderance of evidence leads them to a useful conclusion, or at least shows the scholarship that I put into it that bolsters the points that I make about issues of geography that could mean life or death. Well, they do mean life or death. There are people who die every year lost at sea because of the problems with geography and the mapping and the shape of the Earth. But here you can see this is the most direct train route in Australia from coast to coast, and it covers a distance of 2,331 miles, 3,750 kilometers. Okay. So if you do, so that's just using Google Earth. Here on the Indian Pacific is the name of the rail line. They have it down to the mile because they know their tracks. And they say that it is 2,670 miles, 4,352 kilometers. Okay. So we want to see if that is true. Okay. So if you drove, or if you rode the train nonstop, either way, it's going to take you at a speed of an average speed that they give of 85 kilometers per hour is the speed they give. That's 53 miles per hour. It takes almost 62 hours to cover that distance. Now, I believe that they're saying the number of miles much lower than it actually is, okay? Because in my own experience, like on Amtrak, and I haven't ridden the Australian train, but I think any train is going to be about the same unless it's high speed. In this modern day, the engines are about the same. In my own experience, we were going an average speed closer to, like, I'd say 60 miles per hour, maybe more, because many, many times, if we were on a flat, open space plane, we would go, we would exceed 80 miles per hour. That was the speed limit on our train for the entirety of the journey, because I took a train from Chicago to Emeryville, California. That is a long trip. And then on another one, I went even longer, and then I've driven across country a few times, so I know what I'm talking about here. So 80 miles per hour, I mean, we were going probably closer to 100 a lot of times. And why not? I mean, in the Dakotas and other areas, we went a lot faster. We were stopped a lot. We got sidetracked a lot. And I don't know if they have that problem there, because we were sharing the rails with the freight trains, but they don't count the stop time, I think. So Google says 2,331, 3,750. Indian Pacific says it's longer. They're saying how many miles? 2,074 miles, 4,352 kilometers. Okay. So that's a lot more, but I think it's even higher. It takes skill to trip over flat surfaces. I don't know why that's in there, but it's funny. I have seen people trip on flat surfaces. It's inexplicable. All right. So I decided to look at time zones. Okay. And then we'll come back to the travel distance. But the time zones are sensible around the prime meridian in the rest of the Earth. But you get into this area of the International Date Line and Oceania and Australia, and you get some weird, wacky crap like this. How does this make sense, these time zones? This is convoluted. It's no wonder that it's just a big mess that is hard to navigate there. I really think it would be telling if somebody got a hold of like local maps, the ones that have to be correct, and you lay them out and match them up, make a composite of the physical flat maps, of those islands, and see what comes about with that. But let's take a look here. So Australia is shown in 3 time zones, but it's got that hash mark, and that's because the middle time zone is shifted by an extra half an hour. Why? I don't know, other than just to confuse the issue. But Only a couple other countries do that weirdness. But you can see how, for the most part, the north-south direction of the time zones follow the theoretical, path of the sun evenly, as you would expect, right? So if the map is stretched properly, then it would look like candy stripes or whatever going up and down, right? I don't like candy stripes, just stripes. But I want to point out something here. If you look at the equator, this map, like many other times, I always find the equators in the armpit of Africa, the armpit of Africa. And, it's there and it comes across just above like the point where Brazil sticks out the most, right? It's more than halfway down the page. So that looks funky already. Why they do that is because they're hiding Antarctica. I mean, the southern latitudes beyond 60 degrees, they're off limits. We're not even allowed to look at them on a map sometimes. So let's take a closer look here. If you look at Australia and you go north, so this time zone is at plus 10, okay, in Eastern Australia. Let me see if I can pull up something here. Oh, I couldn't get my pointer. All right, see this area, and you go straight north, and it's 11, okay. Now this area it's got this wacky, it should just be the time zone plus 9, I think. And you go straight up and you get into the 10s, but it should be 9, okay. So that's weird. Where's, this is 10, this is 9 for the ocean, but then you get in the land and it's plus 10. So something's not right there. And then you get in here, this should be plus 8. But if I go straight up, there's plus 8, there's plus 9, and even plus 7. Right here is plus 7. So closer to this edge, it's actually plus 7. So that would indicate wideness, because here you're going from just over here is plus 11. Okay. And on this edge, you have plus 7. So I think this distance has an extra time zone, which is immense amount of land space. It's incredible. Okay. So let's move on to the next slide. So just as I was showing, you even have plus 12. Oh yeah, over here. Here's plus 12 and it reaches all the way over here. And if I go straight down, I hit Australia. So the longitudinal line on this edge of Australia intersects plus 12, and a longitudinal line of this edge of Australia intersects plus 7. So that is 5 time zones. Now, to compare, the United States has four time zones. But you could say 5, but it's roughly equal in distance across to the United States in the respective time zones. Agreed? I mean, here it's shown, it looks like it's only 3, but going by the north-south intersections, 3, that would only be like the western United States, but it's not. It's covering 4 or even 5 time zones. Another way to look at it is at solar noon, you have, it gets obscured by this half hour. So let's forget that. If you take the solar noon, in the middle of these black boxes is the white band. See the key for this? Oh, I guess it's not showing up. But the key for each of these is if the time zone perfectly matches solar noon at noon, it's shaded white, like over here. Let me change my color here. Over here, see this? That's white. So that band is right on, and it's right in the middle of this. So they always match up to that, right? So you have a white band here. I put a black line on it. Okay, and then here, and then here's another one. So that covers 4. If you count this part, it's spanning almost 4. Easily 2.5 time zones. So it's covering 2 complete time zones plus a half on the left and a quarter on the right. So I'm going to say just about 3 time zones according to this data. But actually, I think it's more, and the sun moves faster anyway out there. So that's another factor to consider. But if you go the same distance, you would only get, in the United States, if you go the same distance, you're only going to get from New York to Las Vegas. And you have to remember that the United States is at a higher latitude. We're talking 40 degrees latitude, and Australia is not that far from the equator. So what I had to look at to really get it figured out is just simply the driving distance. So I thought about the Cannonball Run, and the Cannonball Run, or the Cannonball Cup, or the whatever you want to call it. They have a bunch of different names because they have some kind of trademark copyright on the Cannonball name still. But first, just if it's the shorter distance, like they say, like 2,500 miles,
or 2,300 miles, whatever, New York to Las Vegas. That would be closer to what they're saying about Australia. And that's kind of what they're showing with the time zones and the solar noon. But see, we're saying that the sun goes around a greater distance, faster over on, south in the southern latitudes. The sun the sunlight speeds up, and it's possibly due to reflections on the firmament or whatever, how to explain where the sun appears in your local circle of sight. That's not the point of this video. The point is getting the distances. So if we're saying the sun goes faster, then we're at a 6 of one, half dozen of the other situation, neither here nor there. So what do we do? Well, we go and we look at the drive times. Okay. So, if you just look, and this is very telling, if you look at how they actually drive this distance, in the blue line, that's the path they took for this, race. And, the race is officially, only 2,000 miles on the official map. But when you drive it, as the crow flies, it would be 2,050 miles, but when you drive it, it's 2,442 miles. And driving in Australia is not a simple thing like you get on the highway and you go across. I've researched this quite a bit, watching videos, and I really didn't find anything I could use for evidence either way, because there are so many aberrations and anomalies when you're driving with wildfires and roads shut down and washouts, and you've got the outback and you've got mountains and different things that just make you have to detour, and road construction that never seems to be happening, but they'll knock you off the road. You have to go on these back roads, and it's just immense spaces, and you have to detour just to go to a petrol station, and it's just crazy. Like, it's almost set up, you're set up to fail. You can't really just drive straight across, which I found curious. So I dug deeper and I found, okay, here's this Cannonball Cup, Paradise to Perth. Okay. I guess I said Sydney to Perth, but it's Paradise to Perth. Okay. So, they did the race. It's only supposed to be like the equivalent of New York to Las Vegas. And they did it in 31 hours, averaging 142 kilometers per hour, which was including the stops. And there were 3 cars, and the next car arrived 15 minutes later, and the next car arrived 30 minutes later. So that's, that's repeatable. And they did the race several other times, and they got about the same times. Often not reported, interestingly. So it's reproducible, though, because when they did report it, they said, well, it's 4,400 kilometers of a journey, but, the times, okay, 31 hours, just over 31 hours, and that's in the 70s, okay? They claimed that they did 3,000 miles in 29 hours in one run. So it's all very interesting, okay? Here's another one, 32 hours and 22 minutes to cross. I don't know if it's the exact same track or not, but it's more evident, I think, on the next page. Okay, but let's look at the United States. Here, they're traveling across the entirety of the United States, and it was 35 hours and 54 minutes to go 2,863 miles, or 4,600 kilometers, at only 80 miles per hour, which would just be 130 kilometers per hour. And that's one of the early races that's in the 60s, okay? But now it's interesting that the record runs that they had in Australia were just over 31 hours and 15 minutes. And then the record for the Cannonball runs, they also report 140 kilometers per hour, exact same number as in Australia. And they did it from Darien, Connecticut to Los Angeles. Okay, that's a tremendous distance in 32 hours and 51 minutes. So about another hour and 45 minutes at the, right on the same number, which that's a tremendously much larger distance, okay, than what we were talking about before. Now, there's this other race, the U.S. Express, which is from Long Island, New York to Emeryville, California. And again, they averaged around, I think, 140 kilometers per hour, and they did it in 32 hours and 7 minutes. So it's only about not even an hour longer than the Australia race. And you have to understand, in the United States, there's a lot more cities to go through. There are a lot more police and different things to worry about, I think, than in Australia. I could be wrong. You've got the Rocky Mountains. I think that slowed them down. They had to wait. Their road closed at the Donner Pass for, famously the Donner Pass is hard. It's the part of the mountain it's hard to get through to get out west. And I crossed it on a train one time, and it is very steep, and I can see it being a problem for them. So this is another hour, but still, that's a that's another 800 or so miles, although the Australians themselves reported traveling 3,000 miles, I don't know how they worked that out. It's supposed to be closer to 2,000, and the people who actually did the run said they did closer to 3,000. So, looking at the sun path, I had
kind of held on to this image, this map, as being the closest thing to correct. But I'm not so sure. I'm not so sure because of I think Australia is more flattened out, and it may be further over to the left, versus the position that it shows on the map. So going by the time zones and even the position of the sun at noon isn't necessarily the perfect way to do it, because the sun, you do have the analemma, you have to take that into effect, and the fact that the sun travels faster. So we do know that this isn't correct. I mean, for so many reasons. That's long abandoned. It's ridiculous.
Use it to tell me literally anything about the distances between literally anything. Then admit that your map is stupid.
Well, Google, it seems we have your secret. Funny how the North Pole looks, and funny how a sphere is built out of squares, or irregular squares, that have a forced curve, and we know how that's done. We'll look at that later. But check this out. Every video game that I know of, and everyone here, is a flat map, starting with the smallest and going up to the largest. Every road atlas I've ever seen, which is how people got around back in the day, you'd buy this large book and it had rectangular sheets of paper bound together, all of which were flat, and every map on it was flat. And if it had a grid on it, let's say a grid pattern in streets, no matter how far back it was zoomed in a region, it was always flat. Yeah, they had globe pictures at the front and back. Those are the ones you never used. Maybe you'd reference it, but when you were navigating the roads, you used the flat maps on the inside, almost without a doubt. Now, check this out. We're getting into some really large maps here. When you get to Just Cause 2, I think it was, that is like a whole country. Like a small country, but a decent, like a country like Belgium size is what it is. So if you think of these as the tiles, this is how Google Earth was constructed from existing maps drawn in CGI, contoured by drawing in CGI, and then tiled accordingly. And then Minecraft, I guess we passed that, but yeah, here's Minecraft, totally huge, and also totally flat. It's hard to tell, but it's flat. Now, okay, that's just video games. Yeah, you just put things together. Why are they going to bother making the sphere or the curve? Well, let me tell you this. I know now for certain, and I'll show you, how Google Earth was made in the same way, just like the video games. So you have all these maps. Now, some of these already have a curve. They're basically looking like Google Earth. I wouldn't think that they're source maps. You could only have one source map for the curve Earth. I guess, it's a reproducible process, but it's so tedious, I don't think that it was done too many times. But here, with the exception of Bing, you have your European maps and all these other ones. They're all flat maps. They're shown in an ISO view, but they're flat. And then the USGS North American maps, I'm not sure about. I know that the originals are flat in every case across the board with all of these. The world maps. Now here, this shows you how Google Earth was made. They have it as open source. It's Google SketchUp. Okay. When you use SketchUp, it's a Cartesian coordinate system, and you have your 3 axes, X, Y, and Z, and you have a plane. It's planar and it's flat. Now, you take the squares and you build Google Earth, and you can see each one of these shows up that way. Those are the squares. And this little clip shows how you used to have access, or some of us did, some people did, to get in to Google and see this. The overlays, how the tiles, it's called tiling, how the tiles are fit together. Now the tiles are stretched. They're stretched, and then each individual tile is contoured, but the contours are themselves tiled overlays as well. And they match up different pivot points, they're called. So the contours intersect the pivot points. You know those states that are almost square? You know what I'm talking about? Utah, Colorado, the 4 corner states? They are basically square. I've always wondered about that. So Google Sketch. Again, it's just your basic Cartesian coordinate system, XYZ axis, and as proven by drawing a rectangle. So what they do is they move these rectangles to the planar surface and attach pivot points, and sometimes they have to do some bending and stretching of each square or overlay or tile, whichever choice you would like. Usually you start off with the tile and you put your overlay onto the closest side.
And then admit that your map is stupid.
January 24th, 2019, everything seems to be okay for Hawaiian Airlines AJ50, which departed from Honolulu at 4:13 p.m. local time, with predicted landing at JFK at 6:55 Eastern Standard Time. The duration of this flight is 9 hours and 35 minutes. The aircraft type is an Airbus A330. The aircraft was carrying 253 passengers and had 12 crew members on board. Veteran crew member Emilio Griffith doesn't feel well during the flight. Griffith had been working for Hawaiian Airlines for over 30 years, and he's loved and respected by his colleagues. After being flying for almost 3 hours, Griffith doesn't feel better, and the captain decides to make an emergency landing at San Francisco International Airport at around 11 p.m. local time. Although crew members and medical personnel worked hard to save Griffith's life, he dies of a heart attack. He was 60 years old. For the purpose of our research, let's focus on the path of this flight. Hawaii stands at 19 degrees north, 155 degrees west, while New York stands at 40 degrees north, latitude north, 74 west. San Francisco stands at 37 latitude north, 122 longitude west. It's a pretty steep climb to go from 19 degrees north, 155 west to 37 degrees north, 122 west, which is where San Francisco is located, and then remain for almost 5 hours in the same latitude until we reach New York at 40 degrees north, 74 west. Something is not quite right here. Why would a flight that's coming from the southwest not fly towards San Diego or Los Angeles, but fly northwest towards San Francisco and then fly to New York at basically the same latitude? Flat Earth map not only explains why this plane landed in San Francisco, but also gives a better explanation why this plane keeps on flying at the same latitude line for 5 hours, and it makes more sense on the Flat Earth map. We have just seen the strange emergency landing of a flight coming from Hawaii and landing in San Francisco. We can interpret this as being an isolated case due to a death in mid-air, and considering it was one of the crew members, they may have been advised to head to San Francisco by Hawaiian Airlines. But what to say about flight which departed from San Diego in Southern California towards Hawaii but flies to Oakland, California for an emergency landing? This is exactly what happened on October 23, 2018, when Hawaiian Airlines flight AJ37 bound towards Hawaii, Maui, had an issue mid-air when a cockpit light illuminated shortly after takeoff, indicating a possible issue with one of the two engines of the Airbus A321N. According to MercuryNews.com, the plane departed San Diego at 8:25 a.m. and landed in Oakland, California at 10:51 a.m. Still according to the website MercuryNews.com, the airport only received initial reports that the plane would have to divert at 9:30 a.m. That means the plane was already 1 hour into the flight towards Hawaii, heading southwest over the Pacific Ocean when it notified Oakland Airport. The airplane landed in Oakland 1 hour and 21 minutes after notifying Oakland Airport. How could a plane that was 1 hour into a 5 hours and 50 minutes long flight towards the opposite direction of Oakland, California, be able to go back towards the northwest and land the plane in just 1 hour and 21 minutes after notifying Oakland Airport? A direct flight from San Diego to Oakland takes 1 hour and 30 minutes if the flight departs San Diego and fly directly to Oakland. How can a flight that was already 1 hour long towards the opposite direction land in Oakland in just 1 hour and 21 minutes after notifying the airport? This emergency landing does not really make any sense at all when you look at the globe model. Clearly, San Diego would have been the best option for emergency landing if the plane was already 1 hour away over the Pacific Ocean towards Hawaii. But what if Hawaiian Airlines flight AJ37 wasn't flying in that direction? What if Hawaiian Airlines flight AJ37 was already flying towards the northwest? Well, it couldn't be, could it? Isn't Hawaii located southwest of San Diego? Everything starts to make sense when we look at the Gleason's Flat Earth map and compare with the globe model. As we compare the path of Hawaiian Airlines flight AJ37 on both the globe model and on the Gleason's Flat Earth map, it becomes clear why this plane landed in Oakland, California. The flight was already 1 hour into the flight, heading northwest on the coast of California. The pilot notified Oakland Airport, turned the plane to that direction, headed towards Oakland. As we have seen with Hawaiian Airlines flight AJ50, with an emergency landing in San Francisco, and with this flight, Hawaiian Airlines flight AJ37 landing in Oakland, which is just 31 miles apart from each other. These two flights were heading to and coming from the same path as demonstrated on the Gleason's Flat Earth map. The Earth is flat, and flight paths and emergency landings prove this fact. According to Flight Radar 24, Hawaii Airlines Flight AJ51 was flying south of Salt Lake City over Utah when it abruptly changed its path towards the northwest to make an emergency landing in Seattle. The flight was being tracked live, and the flight path being presented here is in accord with the Globe Earth model on Google Maps. All of a sudden, the plane made a 90 degrees turn to its right and headed towards Seattle for an emergency landing. How could that even be possible? As with Hawaii Airlines Flight AJ50 making an emergency landing in the northwest region of the United States, San Francisco, and Hawaii Airlines Flight AJ37 also make an emergency landing in Oakland, California, 31 miles northeast of San Francisco, in the northwest region of the United States, I was not surprised in learning this plane made an emergency landing in Seattle. Most likely, this airplane wasn't even at the place where the tracking software was showing it to be. Not much can be found about this flight or why it went from south of Utah to Seattle for an emergency landing. Nevertheless, we still have to compare the path of this flight as shown in the screenshot with the Gleason's flat Earth map and see what conclusion we get. As compared here, the flight path of Hawaii Airlines Flight AJ51 on the Gleason's flat Earth map is a straight line from New York JFK to Honolulu, Hawaii, having Seattle exactly along its path. We conclude that this emergency landing in Seattle makes more sense when we look at the flat Earth map and makes no sense at all when it's looked at on the Globe Earth model. The path of this flight on the screenshot showing the plane making an abrupt right turn and heading northwest towards Seattle leaves a trail of questions. Why didn't this plane land in Salt Lake City since it was flying south of Utah? How about Las Vegas? Why didn't this flight keep going until we reach Los Angeles or San Diego? What's wrong with Los Angeles? That these flights coming from the southwest always land in the northwest region of the United States? Same thing happens when these flights go from New York towards Hawaii. Just a reminder to you that according to the screenshot, Hawaii Airlines Flight AJ51 was flying at least 200 miles south of Salt Lake City. When we compare all these three flights, AJ50, AJ37, AJ51, this is the conclusion we get. All three emergency landings covered in this video favor the Gleason's flat Earth map over the Globe Earth spinning ball model. All three emergency landings took place on the path of the flights as demonstrated on the Gleason's flat Earth map. All three emergency landings show to be evidence that all these flights fly over the northwest region of the United States, and these three emergency landings were no three consecutive coincidences. All three emergency landings demonstrated that what is being shown in flight tracking websites, sit-back screen of airplanes, and flight tracking applications is a simulation of a globe Earth, another reality of a flat, non-rotating Earth. All three emergency landings demonstrated that what we have known for quite some time, that official agencies hide the true shape of the Earth. Comparing all three flights on the Gleason's flat Earth map, we arrive at the conclusion that these three flights prove when flying straight and directly to or from Hawaii, to or from the northeast of the United States, they all fly above the northwest region of the United States, and emergency landing in cities along the way like Seattle, Oakland, and San Francisco make more sense when we look at the flat Earth map. There are no coincidences here, the Earth is flat and stationary, and we've been all lied to.
Then admit that your map is stupid.
I was reading a lot of stuff on the flat Earth.
Okay, yeah. True.
That's true?
Yeah.
I think it's flat.
Yeah, me too.
We're random flat, aren't we?
Definitely.
We are, aren't we?
Flat as a
Thank
pancake,
you.
mate. Flat as a pancake.
They say flat Earth more than we do.
Yeah.
Yeah. True.
I will tell the whole world you are the weakest link